Okay, let's look at symmetry 2 plane net. As I mentioned, this is the plane net of two-fold symmetry. As I mentioned, that there is lattice points at the corners of this plane net, and this one starting from two-fold symmetry, so all the lattice point has two-fold symmetry elements in there. And I explained to you that there is extra two-fold symmetry developed at these positions. All right, I select that plane net and select another, the same plane net. I would like to put it on top of this. But when you put it on top of this, you have to remember that you should maintain the symmetry elements of these systems. Okay? Because this two-fold rotational symmetry is the vertical symmetry elements. So one way of doing that is I select T3 vector as 0, 0, G, meaning that I put the same plane net just on top of that. Then I see that all the two-fold symmetry is just maintained. Okay? So symmetry elements is conserved. To conserve this two-fold rotational symmetry, one method of you doing it is put the same plane net just on top of that, okay, in the position of 0, 0, G. In this case, this is one crystal system that you can develop. In this case, the lattice points is in here, 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 here. Again, all the two-fold rotational symmetry is preserved. To preserve this two-fold symmetry, meaning that you put the next plane net just on top of that, then this angle should be 90 degrees. So T1 vector, okay, T1 vector and T2 vector and T3 vector can have any arbitrary numbers, and this angle can have any angles, parallelogram. But in this case, the T3 axis should be perpendicular to T1 vector and to T2 vectors. So this is the different type of crystal systems, okay, as compared to the triclinic crystal system. This is what we call monoclinic crystal systems. So this is the second crystal system that I developed. And in this case, there is only one lattice point in a unit cell. So this is what we call primitive monoclinic Bravais lattice. Okay, so if we define how many lattice points in a unit cell, so unit cell shape defines crystal system, but how many lattice points in a unit cell defines the Bravais lattices. So this is basically primitive monoclinic Bravais lattice, or you can write it as 2P. All right, let's think about another way of putting the next level. If I have the first level in here, for instance, and if I put the next level in here, okay, so that this T3 vector goes to half of T1 vector, half of T2 vector. Now G is any arbitrary numbers. Then as you see, all the two-fold system, two-fold rotational axis is now preserved. Okay, so this is two-fold, 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 two-fold. So if you put it on this half G position of the next level of a plane net, starting from two-fold symmetry, then all the symmetry elements is preserved. Okay, so in this case, what I can do is I can define the unit cell like this as T3 vector, something like this. But in this case, basically T1 vector, T2 vector, T3 vector now can have any arbitrary numbers. And now alpha, beta, gamma of the unit cell can have any arbitrary numbers. So in this case, this unit cell is the same as monoclinic crystal system. So if I define the unit cell like this, I lost the information of symmetry. Basically, the unit cell shape looks like the monoclinic crystal system. The definition of that one is basically it has only one-fold symmetry. But this one has two-fold symmetry. So I cannot define the crystal system like this because now I lost my symmetry information. So what you do is instead of putting zero level and first level, I move to the next level. If I put T3 vector like this, then the next level of unit cell should look like this. Okay. Then instead of having these T3 vectors, if I put the T3 vectors move twice like this, then this one is basically I put the same unit cell just on top of that. Okay. So zero level, first level, second level, but this second level is the same thing as just on top of this zero level. Now the T3 vector can be defined as these vectors. Okay, so zero level, first level, T3 vector, but the second level T3 vector, that is the same as the definition of T3 vector in here, so that we can put the same plane net just directly on top of that. And now I can define the unit cell shapes like this. Okay, so T1 vector, T2 vector can have any arbitrary numbers, alpha angle can have any arbitrary numbers, but T3 vector, magnitude can have any arbitrary numbers, but now in this case, I can define that this T3 vector should be perpendicular to T1 vector and T2 vectors. Okay, this one, if I define the unit cell like this, then this one again belongs to monoclinic crystal system. Okay, monoclinic crystal system, and I can maintain the symmetry information in here. This crystal system has at least one two-fold rotational symmetry. But if I doing that, if I define the unit cell like this, now you can see that there is extra unit cell at the body positions. If I define the unit cell like this, then there is lattice points at the corner of the unit cell, which is 1, but there is extra lattice points in the body center position. So this is 2i. 2i is basically, it has at least one two-fold rotational symmetry. So I define monoclinic crystal system, but in order to do that, then there is extra Bravais lattices, which is basically there is two lattice points in a unit cell and extra lattice point locates in the body center position. So this is body-centered monoclinic Bravais lattice. So monoclinic crystal system starting from two-fold symmetry, but there are two different Bravais lattices developed. One is primitive monoclinic Bravais lattice, one is body-centered monoclinic Bravais lattices. Okay, I can define the next level to maintain this two-fold system, T3 vector as half 0g in here. For instance, I put the next level in here, then it maintains the two-fold rotational systems. Again, if I define the T3 vectors like this, then in these vectors, so what I can do is, of course, I can select zero level, first level, and second level. Then the second level basically locates like this, but this one is the same as this. So now T3 vector can be vertical to T1 vector and T2 vector, so it can preserve this two-fold information. So I can define the monoclinic crystal system. But in this case, I may say that, I can define 2B is a B phase-centered monoclinic Bravais lattice. But when there's extra lattice points in here, but if I define the unit cell like this, okay, for instance, as this one T1 vector and this one T2 vector, then basically this extra lattice point again locates at the body center positions. See, in the case of a monoclinic crystal system, T1 vector, T2 vector can have any arbitrary numbers. T3 vector is only perpendicular. So there is no way that I say that this is T1 vector and this is T2 vector. That's different when I define T1 vector like this and T2 vector like this. Basically, that's the same thing. In the monoclinic crystal system, T1 vector, T2 vector can have any arbitrary numbers. The angle between these two vectors can have any arbitrary angles. So it doesn't matter how you define it. Okay. So if I define T1 vector, T2 vector as these prime vectors in here, then this is the same as body-centered monoclinic Bravais lattice, which I defined already. So I don't have to define extra Bravais lattices, either 2B or 2A. That's all the same as 2I, which I defined already. So in the case of monoclinic crystal system, there are only two Bravais lattices. One is primitive Bravais lattice, and one is body-centered Bravais lattice. Right, now define the another crystal systems and Bravais lattices, starting from this symmetry 222 or 2 mm, basically has one mirror planes, which is basically rectangular plane net. Rectangular plane net, as I explained to you, the lattice point locates here. Now this is T1 vector, and this is T2 vector. T1 vector, T2 vector, the magnitude can have any arbitrary numbers. But in this case, this is a rectangular system, so this angle should be 90 degrees. And there is a mirror plane, and there is a mirror plane passing through at these lattice points. There is extra mirror planes, and there is a mirror plane passing through at the 90 angles. That twofold is developed, which I will explain to you later. Okay, so this is based on plane net. If I select it, I select the same plane net and put on top of that. And when you do it, remember, we have to maintain the symmetry elements. So these 2 mm symmetry elements occurs at 0, 0 positions, and half positions here, and half 0 position here, and 0 half position here. So when I put the next level, T3 vector can be defined at 0, 0, G on top of that, and half G, half 0, G, and 0 half G. All right, first select the T3 vector at 0, 0, G, just to put it on top of that. So I can define the unit cell like this. So the unit cell is starting from the rectangles and put it on top of that. So unit cell is defined like this. Now all this angle is perpendicular each other. T1 vector, T2 vector, T3 vector can have any arbitrary numbers, but all the angle is now 90 degrees. So another crystal system is defined, which is 222, this is orthorhombic crystal system. Okay, orthorhombic crystal system has 3 axes at any magnitude, but all these 3 axes should be perpendicular each other. Now, when I define this T3 vector like this, then you see that there is only one lattice point in a unit cell. So this is primitive orthorhombic Bravais lattice. So one crystal system is defined, and one Bravais lattice is defined. So if I put it T3 vector at half G, then the first level lattice point is here, and the second level next point is here. Okay, so if I define the T3 vectors like this, now this T3 vector has any arbitrary angles with T1 vector and T2 vectors. So it lost the information of the plane net, which has mirror plane and perpendicular twofold. So 2, 2, 2, we have to define the new crystal system, which is orthorhombic crystal system. But if I define the T3 vector like that, then this one looks like monoclinic crystal system. So it lost the information of the symmetry. So instead of doing that, I have to select another levels just to put it on top of that. Then the next level looks like this. So then this one is the same as this. So in this manner, I can put it directly on top of that. So all the angles is now maintained 90 degrees. So it preserves the information of symmetry. Okay, so this is orthorhombic crystal system. But when you're doing that, there is an extra Bravais lattice developed because there's a lattice point at the body center positions. So this is 222I. This is body-centered orthorhombic Bravais lattice. Right? If I do this T3 vector at 0 half G position, then the lattice point is here, here, here. Now the first T3 vector is defined here, so the angle is not perpendicular, so that we have to define the next levels and then put it directly on top of that. Then because of this second level lattice points, there is extra lattice points located at the center of A phase. Okay, I cannot define the T1 vector and T2 vector like this, as I explained to you about the monoclinic crystal systems. Okay, monoclinic crystal systems, because in this case, the T1 vector and T2 vector cannot have 90-degree angles. So this is something you cannot do it. So you have to find out that the extra lattice points located at the center of A positions. Okay, so 222A is developed. So 222 develops orthorhombic crystal system, and 222A is A phase-centered orthorhombic Bravais lattice. Okay, so why not I222? Because T1 vector, T2 vector should be 90 degrees. So I cannot define the T1 vector, T2 vector in these manners as I did in the case of monoclinic crystal system. Okay, if I put another lattice points like this, then of course you can say that 222B, B phase-centered orthorhombic Bravais lattice is developed. But in the case of crystal structure, who can define x-axis and y-axis? Okay, so x-axis, y-axis, y-axis, x-axis is the same. So basically 222A is the same as 222B. So B phase-centered orthorhombic or Bravais lattice is not defined. It's the same as 222A. Now let's start from the diamond plane lattice. Again, diamond plane lattice, the lattice points located in here. Of course, the locations of symmetry elements of 2 mm is at 0, 0 positions or half and half position. Okay, this position and this position is where the symmetry of 2 mm locates. So when you put the next level, you can select the displacement vector of T3 at 0, 0, g and half, half g. Okay, so let's put the next level at 0, 0, g. Then you think that the lattice point is here and the T3 axis is now perpendicular. But basically, a rectangular system and diamond plane net has basically the same symmetry elements. It's just a matter of how you define your lattice points. So in the case of symmetry elements, these two different plane net is basically the same thing, okay? Only if you think about the symmetry elements. So instead of building this T1 vector and T2 vector and this diamond with some arbitrary angles, what I do is, instead of doing that, I define the unit cell like this to make T1 vector and T2 vector perpendicular each other. Then I put the next level directly on top of that. Then this unit cell is all interrelated. Okay. So basically in this case, what I can see is I can define the same orthorhombic crystal system, but let's say C phase-centered orthorhombic crystal system. But C phase-centered, A phase-centered, B phase-centered is basically the same in the crystal structures of the orthorhombic crystal system. So this is the same as 222A, A phase-centered, which we defined already. Okay, so no new Bravais lattice is developed. Now let's think about T3 vector, put it half G position. Okay, so the first level, for instance, locates here. Then the second level locates in here. And the third level, of course, locates in here, like this. Then by the same token, I define the T1 vector like this and T2 vector like this, because it's the same as orthorhombic crystal system. The symmetry information is still there. And I cannot define the next level T3 vector as half G because it's now inclined, so it lost the symmetry information. So instead of selecting 0 level and first level, I have to select the second level. So just put it on top of that. So in this case, the unit cell is defined like this. Okay, so put it on top of that and define it. Then now you see that all the extra lattice points locates at the center of all the faces. Okay, in the bottom there is extra lattice points defined in here, here, and where, and here. Now this extra lattice point is the center of this, for instance, A face. This extra lattice point is center of this B face, something like that. So in this case, if I define T1 axis in here and T2 axis in here, for instance, I set T1 prime and T2 prime and T3 vector as perpendicular, so the same as defining orthorhombic crystal system. Now I found out that there's all the extra lattice points at the center of each faces. So new Bravais lattice is developed, which we call 222F. 222 defines the orthorhombic crystal system. F defines face-centered orthorhombic Bravais lattice. So there are 4 different types of Bravais lattices can be developed in these orthorhombic crystal systems.